In this section of Chapter 8, I would like to go over homework problems on resonance and also exception to octet rule, and also discuss additional Lewis structures. Let's go over problem number 56, page 325. In question number 56, it says that based on Lewis structures, predict the ordering of NO bond lengths. So NO, question is asking for NO bond lengths. In NO plus, NO2 minus, so let's write down here NO plus, NO2 minus, and NO3 minus. Okay, along the way, when we solve this problem by drawing Lewis structures, I'm also going to write down what kind of bond character or bond order it has. By bond order, we mean what kind of bond is that? Is it a single bond, double bond, triple bond, or something in between, single and double or double and triple? So let's begin with NO plus. Again, since this is going to be Lewis structure, so first we need to get valence electrons. Nitrogen has 5 valence electrons. We all know that this is the outermost electrons. If you look at periodic table, 2s2, 2p3, so s and p electrons, or you can just count from left to the right along the same line. Nitrogen is the 5th element, and that's how you get valence electrons. Now we have oxygen. There is one oxygen that has 6 outermost electrons. That makes 11, but don't forget that NO is plus 1. That means 1 electron has been removed. So you have 10 valence electrons. So this is valence electron. Now let's draw the Lewis structure for NO. Nitrogen is less electronegative, so let's treat this as the central atom, oxygen the outer atom, and joined at least by a single bond or one pair of electrons. Now give noble gas configuration to outer atom, which is oxygen, and I need to add 6 more electrons. So each line, small line, would be a pair of electron, 1, 2 pair, 3 pair. That gives 8 around oxygen. Now I have altogether 10 valence electrons. So extra electron, the 2 electrons that I have, that needs to be placed on nitrogen, because oxygen has already octet or noble gas configuration. But now by looking at nitrogen, you see here nitrogen doesn't have 8 electrons. So in order to make it 8, what you could do is you can bring in electron pair from oxygen to in between. Okay, so I end up with a structure like this, N triple bond O. Now let's count around each atom. Now we have 8 electrons on both nitrogen and oxygen has noble gas configuration. So N triple bond O is the Lewis structure for NO plus. Now let's work on NO2 minus. So let's draw a line here. Nitrogen has 5 valence electrons. Each oxygen has 6 times 2, that's 12 valence electrons. Now we have 17, but keep in mind NO2 is minus 1. So there is an additional electron. So that makes it 18 valence electron. Now we need to account for these 18 valence electrons. When I draw the structure, let's have the central atom nitrogen and 2 outer atoms. We don't know the shape at this point, so it doesn't matter how you write down. And Lewis structure doesn't care about the shape. Okay, now I need to give octet to the outer atoms, in this case those 2 oxygen atoms. So let's do that. 2, 4, 6. That makes 8. 2, 4, 6. So that's 16. I have 2 additional electrons in, and we need to put those 2 electrons onto nitrogen. Now I have accounted for all 18 valence electrons. But only problem is nitrogen has only 6 electrons and it's supposed to have 8. And we know how to deal with this issue. Bring in a pair of electrons from either side of the oxygen. Okay. In between. And that gives me a structure. Let me show you the structure that I'm going to get now. Would be N double bond O on one side, single bond O on the other side, and we have 2, 4, that's fine, and then we have 2, 4, 6. Don't forget that we had a pair of electrons on nitrogen. So this is one of the structures for NO2. Let's call it structure number 1. When I created structure number 1, I could have brought electron pair from the left-hand side oxygen too. So let me show you what I mean by that. I could have had this pair of electron brought in between nitrogen and oxygen. In that case, I'm going to get the second structure, which I'm going to show now. And this time O would be on the other side, but with the double bond, single bonded O, 2, 4, 6, and here you'd have 2, 4. And we'll call it resonance structure number 2. These structures look similar, but they're not identical because the double bond location is different. In structure 1, double bond is on the right side, and the structure 2 is on the left-hand side, oxygen. So actual structure to be given by the combination of these two. Now let's now focus on what combination may give you. In first case, we have a triple bond. We call it bond order. So bond order in first molecule, NO plus, is 3 because it's a triple bond. In second structure, which would be the hybrid of 2 structures, 1 and 2, they're called resonance hybrid. And what kind of bond order between nitrogen and oxygen? So NO bond order. So bond order equals to, are you going to call it 2 or 1? Because on one side there's 2 and other side is 1. Truly it's neither of those because the second bond is moving around. If you think about the combination of these 2 structures, and if you focus on this double bond, that double bond is 2 places. It runs between right side oxygen to left side oxygen. So when you combine it, you're going to have an average effect. So one of these 2 bonds is fixed. So one is already fixed, one bond is fixed. But the other one, the second bond, is moving in 2 places. It's like you have $1, but you're sharing between you and your brother. So each of you get a share of half of that. Now in this case, same is the case. You have one bond being shared by both sides oxygen. That's why it's flipping from right side to the left side, and that would happen. And that's why average would be 1/2 of that bond on each side. So bond order is going to be 1 and 1/2 or 1.5. Let's now work on NO3 minus. Valence electrons for nitrogen is 5. Each oxygen is 6, and we have 3 of them, 18. That's 23. Now there is an additional electron because NO3 is -1. So that means there is an additional electron. Altogether, we must account for 24 valence electrons. So let's write valence electron. Now central atom is nitrogen and outer atoms are oxygen. So nitrogen, oxygen, oxygen, oxygen. Now give noble gas configuration to outer atoms. If we count Number of electrons 2, 4, 6, 8, 2, 4, 6, 8. So that's it. That's 24. This accounts for 24 valence electrons. Now I don't have any more electrons to be placed. I don't have any more electrons to place on nitrogen. So nitrogen, central nitrogen, has only 6 electrons. So we know how to make it 8 by bringing a pair of electrons from oxygen to in between nitrogen-oxygen bond. Now it doesn't happen, so there are 3 possibilities, and all those 3 would give rise to 3 resonance structures. So let me show you those 3 structures. So when you bring in from here to here, you're going to get, I don't have too much space here, so I need to manage some space. So it'd be double bond here, single bond here. So that's 4, 6, 8, 2, 4, 6, 8, 2, 4. So this is our structure 1. Our structure 2 would have a double bond in different location. So let's write down that. And double bond O, single bond O, single bond O. So that's it. 6, 8, 2, 4, 6, 8. That's our structure 2. Let's use a different color so that we have better idea. And a structure 3 would have N double bond O on the left side. So it's going to be N double bond O, single bond O, single bond O. 2, 4, 6, 2, 4, 6, 2, 4. Okay, now we have all these 3 resonance structures. Let's draw a line here. Let me identify those. You can see in the red, I have identified those 3 resonance structures for NO3 minus. Look at the location of the double bond. The double bond is moving around among how many places? The second bond is moving around 3 places. Those 3 places are NO. There are 3 oxygens. So actually that's second bond or double bond is moving around among those 3 sites. So if I said that actual structure is combination of these 3 structures, 1, 2, and 3, what kind of NO bond order you're going to get? Is it a single bond, 1? Is it 2? Is it 3? No. One bond is fixed. So bond order, let me write down here, bond order has to be more than 1 because 1 is fixed. The second one is moving among 3 places. So it has to be distributed or equally shared in 3 places. So each site, NO site, is going to get 1/3 contribution. So it's a 1 and 1/3. So I'm going to write down 1.33. Okay, now bond order or bond strength is determined by this bond order. Larger bond order means greater bond strength. Now, how does it go with the bond length? Keep in mind, bond is nothing but force of attraction. Having 3 bonds, first molecule had bond order 3. Having bond order 3 means its strongest bond. There's a greater attraction working there, and N and O would be getting closest. So NO distance would be shortest. So let me write down here, NO shortest. Then 1.5 would be the next one, and 1.33 is the weakest of all these NO bonds. So NO distance would be longest. So write down here, NO longest. So if you want to organize this, NO in NO3 minus would be longest, followed by NO distance in NO2 minus, and then it would be NO plus. That would have the shortest distance. So this is how you can organize NO bond lengths based on Lewis structures. So keep this in mind. The longest one would be, so it depends upon how you organize them, shortest to longest or longest to shortest. If you start from the shortest, then NO plus followed by NO2 minus and then NO3 minus, which would be the longest one. Okay, if I organize from largest to smallest, so you can write down like this. Let me use this here. NO plus, that will be the shortest. Let me use this sign. This is bond lengthwise. NO3 minus would be the longest. Let's go over number 63, chapter 8. And this is Brown Lemay Barston book, 12th edition, page 325. So this is page 325. Now first I'd like to go over B. So the question is, identify, first you need to draw a Lewis structure, then identify those that do not obey the octet rule and explain why they do not. We'll begin with AlH3. Aluminum. If you look at the location of aluminum in periodic table, aluminum is under group 3A, or you count it from left to the right along line 3, it's the third element, and that gives us valence electrons. So 3s2, 3p1. So valence electron is 3. So aluminum has 3. Each hydrogen has 1, and we have 3 hydrogens. So altogether we have 6 valence electrons. And let's write down the central atom. Central atom, hydrogen cannot be a central atom, so because hydrogen cannot have more than one bond. So Al, H, H, H. Now whenever you draw a single bond with hydrogen, it gets the electron configuration of helium, and it cannot have 8 electrons. So that's always is the case. Now what about the central aluminum? In this case it has 6 electrons, but it would like to have 8, but it doesn't have any additional electron. We don't have any additional electron to place on aluminum. So there is no other choice rather than having this structure. So AlH3 would have aluminum with 6 electrons around and hydrogen with only 2 electrons around. So both hydrogen and aluminum would violate octet rule. Okay, now we're going to do now another problem, which would be C. That's for N3 minus. Each nitrogen has 5 valence electrons. Again, look at periodic table. It would be in line 2, so it'd be counting from beginning of that line until you get nitrogen. Only S and P electrons. So 1, 2, 3, 4, 5. So nitrogen has 5 valence electrons, and there are 3 of them, 15. And N3 is minus 1 because there is an additional electron. So altogether there are 16 valence electrons. Now with 16 valence electrons, now we need to first write down the Lewis structure and then assign these 16 valence electrons. So nitrogen, let's put nitrogen in the middle in the first structure. One nitrogen on the one side, the other nitrogen on the other side. Give noble gas configuration or octet to outer nitrogen, and that makes it 16. Now what about the central atom? Central atom doesn't have 8 electrons, and we do not have any additional electron to place on the central atom. So in this kind of situation, what you need to do, there are several things you can do. that would give rise to three possible structures, and we'd call them resonance structures. I can bring a pair of electrons from this end to in between and from other end to in between. Now this would give me, let me draw that structure, N, double bond N, double bond N, and let's write down the other electrons, 6, 8, 6, 8. So this is our resonance structure 1. I can also have, rather than bringing electron pair from, say, right side, we can have two pairs of electrons coming from the same nitrogen and nothing coming from the other side. So if that happens, what am I going to get? Let me show you that. I'm going to get a structure like this: N, triple bond N, single bond N, 2, 4, 6, 8. So that gives me a structure number 2. Now this can also happen on the other side, triple bond on the other side. That would give me a structure number 3. So let me write down that. Central N, triple bonded nitrogen, single bonded nitrogen, and 8. So this is my structure number 3. Structure 2 and 3 are very similar, except that triple bond in one case is on the right side, and in the other case triple bond is on the left hand side. These 3 are resonance structures, and in none of these cases we exceeded octet rule. Or in other words, octet rule is valid for each nitrogen in each of these resonance structures. So actual structure of this compound N3- would be given by this combination of all these 3. Now we're going to do now 63E. Question is SbF5. Sb, if you look at periodic table and look under nitrogen group, which is 5A, Sb is antimony, and you know that 5A element, just like nitrogen, outermost electrons would be 5, S2p3. So they all have S2p3 outermost electron configuration. So antimony would have 5, each fluorine would have 7, and we have 5 of them, that's 35, and altogether we have 40 valence electron. Antimony would be at the center, so let me write down now Sb, and there are 5 fluorine. 1, 2, 3, 4, 5, and give noble gas configurations. Now I can count whether I have assigned all the valence electrons or not. Each fluorine has 8 around, so 5 of them would have 40. So I have assigned all those 40 valence electrons. But what you see here is the central Sb has too many electrons, and we have no choice. So whenever there are 5 bonds, it's going to break the octet rule. So in this case, each fluorine would have 8 electrons, but antimony would have 10 electrons. So it doesn't go by the octet rule. Now we're going to go over number 64, page 325. Again, you need to draw Lewis structures and identify which atom doesn't obey the octet rule in these molecules. So I'm again randomly picking a few of these, like C is asking for ICl2 minus. So C is ICl2 minus. iodine is coming from group 7A. Again, when you're doing this, make sure you have a periodic table in front of you. 7A, all these elements would have outermost electrons same. Outermost electron number should be the same as fluorine. So it would be 7. These are from group 7A, 7 valence electrons. And each Cl also belongs to the same group, would have 7. And there are 2 of them, that's 14. Altogether we have 21. And since ICl2 is -1, there is an additional electron. So we must account for 22 valence electrons. Now I is the central atom. Let's write down. And 2Cl. It doesn't matter how you draw these because we don't know the shape at this point. And give noble gas configuration to the outer atoms. For 6, 2, 4, 6. That makes 16. Then 18, 20, 22. So now I'm done with the Lewis structure. Only thing is central atom exceeds 8 electrons. And that's okay because you have no choice. You have that many electrons. Normally, when you need to break the noble gas configuration or octet rule, break it for the central atom rather than for outer atoms if it is element other than hydrogen. Okay, so that's, in this case, both each Cl would have 8 electrons, but I would have more than 8 electrons. So you can see that there are 1, 2, 3, 4, 5 pairs with 10 electrons. Let's now try D, problem number D. In problem number D, they gave you OPBr3, but they're saying that P is the central atom. So OPBr3. Let's write down all the valence electrons. Oxygen has 6. Phosphorus is the same group as nitrogen, has 5. Each Br has 7, and 3 of them would have 21. 26, 32, so you have altogether 32 valence electrons. Now they're saying that P is the central atom, so just put pressure P on the central atom as central atom. So P, the central atom, and oxygen, then 3Br, 1, 2, 3Br, and give noble gas configuration to the outer atoms. So let me show you how to do that. 2, 4, 6, 2, 4, 6, 8, 2, 4, 6, 8. So that assigns all 32 valence electrons that we had. And phosphorus, the central atom, also had 8 electrons. So there is no violation of octet rule. So they all obey octet rule. Now let's try E. I don't have any more space, so that would probably be the last one. XCF4, xenon tetrafluoride. Normally, noble gases don't give any compound, but the larger ones, which are highly polarizable, and they do give some of the compounds like XCF4, XCF6. Now, XC, xenon, is from group 8A, and they all have 8 outermost electrons, S2P6, 8 valence electrons. Each fluorine has 7, and we have 4 of them. So 7 times 4, that's 28, and altogether we have 36 valence electrons. So let's draw the central atom and the outer atoms. X is the central atom, and let's put down other 4. and then give noble gas configuration to fluorine. By single bond, I already gave each a pair of electrons, so 2 4 6 2 4 6 2 4 6 2 4 6. So now around each fluorine I have now 8 electrons, and we have 4 of them. That's 32. So 34, 36. Those are solely on xenon. So even though each fluorine obeys octet rule or noble gas rule, but central xenon has 5 pairs. I'm sorry, there are 6 pairs of electrons. So that went over octet. Because you have no other choice. You have that many valence electrons, so it has to be placed on the central atom rather than the outer atom. So again, here you're seeing that central atom doesn't obey the octet rule.